Yeah, so good old AC is a positive feedback. And I have one that was not in your book. It's called a rose. Rain on snow event. Rose. People who know snow, like if you're a skier or snowboarder, or you live in Mammoth, or you visit Mammoth regularly, like snow addicts, you understand the worst thing that can happen to snowpack is a random rain in the middle of the winter. For one thing, rain will melt your snow away. For another thing, that rain in the winter will freeze and make a layer of ice, which causes additional avalanches later. And when water runs through snow, it carves gutters into the snow, which become icy chutes that funnel snow from high elevation down to where it's more likely to melt. How many of you understand this from visiting snow mountains? That this is sort of something you kind of get. Makes sense? So here's the funny thing. It doesn't have to be enough global warming that Mammoth lacks snow. It just has to be a little temperature burp that the snowstorm on March 13th is a little bit too warm, so it turns into a rainstorm. For example, if it rains in Mammoth today, that probably means the beginning of spring conditions. You'll lose a lot of snow. And here's the problem. Here's why it's positive feedback. As soon as you've exposed the dirt underneath, now you're going to start heating the ground and heating the air. So because we know that Greenland is getting a couple more rainstorms and a couple less snowstorms, this is the main reason that Greenland is melting. It's not actually the temperature. It's the fact that the period of snow accumulation is cut off by this late rain and this early rain. So now you're only building snow for this part of the year, and then you're melting for the rest of the year. Does that make sense to everyone? It's like one more fall rain and one more spring rain. They shrink your winter. Without making the planet any hotter, just a couple of fluke storms and a couple of fluke storms, you've got less winter to build snowpack. So instead of growing glaciers, you have shrinking glaciers and a heating planet because you've exposed the dirt more. You have less albedo, more heat. Does that make sense to everyone? Rain on snow events?
Yeah.
A long time ago, we used to worry about how heating would cause snow to melt. Now we realize it doesn't need to be hot enough to melt the snow. It just needs to be hot enough to have a later rain or an earlier rain. And that threshold is way lower than making it hot enough to melt Greenland. Yeah.
Really quickly, when you were talking about the negative, when you said that there's more water vapor, more snow, the ground's more reflective, so it adds albedo. How does that work?
Because albedo increases the amount of light reflected, which shrinks the amount of light absorbed. Don't forget that light is the key ingredient that will become heat when it gets into the ground, right? Light is not heat on its own. So if you can block the light, you're not going to get the heat. Snow is shiny. Dirt is not shiny. Imagine if you're wearing a black sweater in the sun, you're going to get really hot. But if you put a mirror over you, who cares about your sweater? There's no light hitting you. Does that make sense? So soil is dark. Soil absorbs light and makes it into heat. But if you put snow over that dirt, it's never going to absorb light. Yeah. Everybody got my positive and negative feedback? I did them negative first and positive. Rose, rain on snow event. Albedo is reflectivity. Anything else on number 22? Yeah?
Are any negative feedback loops actually having a major impact?
The increased algae thing is really significant. On the flip side, it's kind of a bummer. We're doing other stuff to the ocean that's kind of tweaking the algae. So if we weren't having other pollution impact in the ocean, the algae thing could help us a lot more. But because pH is changing in the ocean so quickly, it appears that the algae negative feedback is sort of being canceled out by algae decline specifically. So we would be getting a lot of negative feedback from the algae if we weren't shooting ourselves in the foot by killing the algae. Okay. Anybody want to talk more about number 22? Because I've got something in number 23 that the College Board always asks you about. Guaranteed to be on the AP test. It's called ENSO, which stands for the El Nino Southerly Oscillation, or ENSO. In California, everybody calls it an El Nino, just El Nino. But internationally, most people know it as ENSO, E-N-S-O, for the El Nino Southerly Oscillation. And I'll explain the oscillation soon. Before I can explain, please look up this confusing drawing and this confusing drawing. I got to remind you about this confusing drawing. I think you'll remember, but I got to show you visually. Remember we talked about how a convection cell works, hot air rising, cold air sinking. Then we also talked about how there are 6 on our planet just because of the size of our planet. Then we talked about how most of the heat is at the equator, so the wheels spin past each other. Then we spun the planet under the convection cells, and we explained the trade wind and the westerly wind. You guys remember that? Now, here comes the detail where most of my students fall off the back. Watch. The trade wind pushes west across the equator, both in the northern Pacific and in the southern Pacific. Everybody see that? If you are a sailboat standing in Ecuador, the trade wind will push you straight across the equator to Indonesia. Does that make sense? If you go a little north of the equator, the northern trade wind. If you're a little south of the equator, the southern trade wind. So combined, there's 2 separate trade winds pushing across the equator. Everybody got that? Now imagine this is my giant cleaver of death. And I will chop the planet in half. And then I will flip the planet sideways so you're looking straight into the South Pole. Everybody got that?
Which half of it?
It doesn't matter. You're looking at a slice of the equator. Everybody got that? When you look at a slice across the equator, the planet tipped up on its side, you would have Ecuador on the right, the equator as your visual horizon, and Indonesia on the left. Do we agree?
Mm-hmm.
Because that slides across the equator, so I've got Ecuador on one side and Indo on the other. Everybody following me? Because this is the part where some of my students are confused. What we're looking at here is that planet cut across the equator with Ecuador on the right side and Indonesia on the left. Sort of bridging where that flat map would meet in a sphere. So, first, the normal conditions. If you could please look up, normally a trade wind blows west. Remember that? The trade wind blows west. And so, hot equatorial surface water is blown west toward Indonesia. Offshore winds in Ecuador make upwelling, and hot water pushed west means you've got a lot of water vapor and rain in Indo. If you've got a lot of water vapor here, you know that there will be cold, dry air on the other side, just like this. Across the equator, because the planet is spinning and you get a Coriolis effect, you've got hot water migrating, evaporating, raining, and dropping as cold air back to the equator to get pushed over it. Does that make sense to everyone? This is called the La Nina phase, or La Nina cycle, and it is the majority of years. 80–85% of the time, the Pacific Ocean is in what's called the La Nina phase. It is the normal status of the Pacific Ocean. And technically, I think that's also true in the Atlantic, but the Atlantic is so skinny at the equator that it's almost irrelevant to the Atlantic. Now, for reasons that nobody understands, and I'm sorry to say, I've heard a lot of explanations and I just didn't understand them, but I don't think that there is a scientific consensus yet. Sometimes, poof, the trade wind disappears. That angry cloud just goes away. We don't know why. One explanation I have heard, if anybody wants to nerd out, like watch this. If you don't want to nerd out, just earmuffs for like 1 minute. For all you nerds, there are periods when there's more water vapor in the atmosphere. It might be caused by global warming, but it might not. With more water in the atmosphere, the Coriolis effect is technically a little bit tighter. So the trade currents, instead of skimming the equator, go north of the equator and south of the equator. So the trade current at the equator is weaker. For all you nerds, it's because the Coriolis effect kind of shrinks to the middle of the ocean. And it's probably because of the specific heat capacity of the atmosphere changing. For everybody who was wearing earmuffs, it doesn't really matter. Nobody can explain that anyway, so who cares? For some reason, you get no trade wind. So look what happens to the water in the Pacific. It stays in the middle. With no offshore wind, you get no upwelling. And with no with no trade wind, all the evaporation happens over the mid-Pacific. You get all your rain in the middle of the ocean. That means there's less rain falling on their side, but water vapor is closer to us, so we are relatively wetter because we're closer to the clouds. We get to keep some of the moisture that would have been pushed across the ocean by the trade. Does that make sense to everyone? If you have trouble remembering the explanation for an El Nino, don't forget, the Americas are more wet in an El Nino. And you know that because Santa Barbara El Nino years are really wet. Anybody remember our more recent 1995, 1998? Were you alive in 95? Yeah. God, I was like enjoying the surf that year. I have like distinct memories of early adulthood. What? Technically speaking, I am old enough to be your father.
Oh, Jesus, I've been wondering about this beard for a long time.
Oh!
That's been like true for like the rest of the time.
Guess so, but it just hadn't quite sunk in.
everybody like
Oh my God. I gotta go buy a Trans Am.